The following is a multi-logic gate circuit. The small grid on the right is the CPU. Colors represent yellow, input, orange, output, green, memory, blue, logic. Large orange timer blocks on the left are the outputs, from right to left, and gate plus NAND below it, or gate plus NOR below it, XOR gate plus XNOR below it. And triggers when all the inputs are true, or triggers when at least one input is true. XOR triggers when at least one input is different than the others. In the CPU, small timer blocks serve as memory, while the event controllers handle logic. Buttons control the input blocks. Button 1 switches the rotor lock. Button 2 reverses the piston. Button 3 toggles the door state. Button 4 turns the beacon on and off. A group of event controller called converters translate the input block states, rotor angle, piston position, door state, beacon state, to the corresponding memory timer on-off state. How to set up the logic event controller will be explained later. This is an example of a practical XOR gate use case. The rotor lock on action and the rotor lock off action. Normally the vanilla game only has the on-off action. Buttons control the state of the leftmost memory timer, while the right timer is synced with the rotor lock state. The XOR circuit detects when the two timers have different states and toggles the rotor lock and the corresponding timer to keep the states same. Adding a delay timer should make it more clear. This is a 6-bit binary counter. It can count from 0 to 63. Setting this up is easy. The event controller checks the state of the timer on the right, and when it turns off it toggles the state of the timer on the left. You continue the chain to add as many bits as you need. To trigger something on a specific number like 10, which in 6-bit is represented by 0, 0, 1, 0, 1, 0. You need to add extra memory timers to represent the ante-state of some digits. In case of 10 it is the first and third digit from the right, then you perform the AND logic for the last 4 digits from the right, using the ante-state timers instead of regular ones when available. During editing of this video, I discovered that I accidentally used start action instead of trigger now action in the reset timer. This is why the counter resets at 11 instead of 10. Now we will learn how to set up the logic gates. Since it is rather abstract, it is required to keep a consistent block naming system. Color coding the blocks also helps. The colors represent yellow, input, orange, output, green, memory, blue, logic. First we set up the converter event controllers. Their job is to translate the input block's state to the memory timer state. In this example we are comparing the beacon on-off state with the piston position state. We select the event from the list, then add the monitored block, and finally set up the actions. In the first action slot we turn the corresponding memory timer on, in the second action slot we turn the timer off. Now we set up the logic event controller, in this case, AND gate. We switch the AND gate checkbox on, then we select the block on-off event, and add the memory timers which are named state. Once that is done we set up the actions for the output timers. The AND gate returns true when all inputs are true, so in the first action slot we turn the output timer on, and in the second slot we turn the timer off. We do the reverse for the NAND, aka NOT, and in the second toolbar. The upper output timer is for the AND gate, while the lower is for the NAND gate. For the OR gate, the setup process is similar, however the block on-off event has limitations. In this case, the memory timer need to represent the ante-state of the input blocks, which means that when the input block returns true, the memory timer must be off. We do this by turning the timer off in the first action slot, and turning it on in the second action slot. The ante-state memory timers are represented by having false in their name. To work around the bug, we need to use AND logic to build OR logic. The expression is the following. If all the inputs are false, then return false, else return true. This is the same as saying, if any input is true, return true. So we enable the AND gate checkbox, add the ante-state memory timers to selected blocks, then, in the first action slot we turn the OR output off, and in the second slot we turn the OR output on. We do the opposite in the second toolbar for the NOT OR output. The XOR gate, aka exclusive OR, is more complex. It has to be built with 3 logic gates: NAND gate, OR gate, and gate. It also requires more memory timers. You need both the regular state and the ante-state for each input. You use the multi-toolbar feature in the event controller to set this up. You set up the NOT and, like in the AND gate example, using the regular memory timer states, turning off the NAND state in the first action slot, and turning it on in the second slot. You set up the OR gate using the memory timer anti-states, turning off the OR state in the first action slot, and turning it on in the second slot. Finally, you perform the regular AND operation on the outputs from the previous two gates. The exclusive OR returns false when all the inputs are the same, and returns true when at least one input is different than the others.